Put simply, the way we build our towns and cities needs to change. The construction and operation of current buildings accounts for 40% of the world's energy consumption and approximately 1/3 of greenhouse gas emissions. But could one of the oldest building materials known to humankind form part of a modern solution for our buildings and cities of the future? A global technological revolution is underway.
We think in the next 10 years, you'll see more innovation than we've seen in the past 50.
Driven by passionate, dedicated individuals intent on shaping a new world.
I want to create something new. I want to create something that gives me the sense of creating new life. This is why I'm here.
A greener world.
This is the last call to action, that we have to develop the solutions that are protecting our planet.
A better world.
I have a family, and when I think about the life I want them to have and their children to have, I want them to experience the world where they can travel and live without worry, and that gets me up and going every day.
Together, they are pushing engineering to its limits.
Human creativity is the most tremendous power, and if you set a target, things that you never thought possible become possible.
Creating extraordinary machines that can help the planet and humankind in the future. Architect and historian Professor Maxwell Hutchinson has not only been designing buildings for half a century, he's also been involved in their conservation, some of which date back over 1,000 years. He's one of a growing number of people within the construction industry who believes that the huge carbon footprint associated with our current use of building materials, such as concrete, is unsustainable.
There is general consensus that we need to change the materials we use in building all of our buildings. There's a huge amount of embodied energy, that is to say, the energy that goes into making the material, transporting the material, and putting it into position. And Portland cement, which is the principal ingredient of concrete, is incredibly energy intensive.
It is estimated that annual cement production currently accounts for around 8% of global CO2 emissions. And what the cement is mixed with to create concrete further compounds the ecological damage.
Every year, the construction industry uses 50 billion tons of sand. That's enough sand to cover the United Kingdom.
And the problem is that the world is running out of the right type of sand. The wind-worn granules found in deserts are far too smooth to bind together to form stable concrete. So acute is the shortage that all over the world, riverbeds, beaches, forests, and estuaries are being stripped bare, often by organized criminal gangs operating on a vast scale, with lethal consequences for those who oppose them. But what if we could find a sustainable way of using an extraordinary building material, one that as part of its production process actually absorbs carbon? Well, the good news is, we can. In downtown Milwaukee, we might be seeing a glimpse of the future. Amongst much media attention, a groundbreaking ceremony is underway. Normally, this takes place before even a shovel breaks the earth. But this is no ordinary build. Although concrete foundations, parking floors, and lift shafts have been completed, for those involved in this project, it's all about what comes next.
If it's not been apparent, literally words cannot describe the excitement I feel about being here today.
Property developer Tim Gochman never intended to make history. He just wanted to make a building that people wanted to live in. Standing 284 feet tall, Its 25 stories will house 259 luxury apartments, a pool with retractable walls, even an outside cinema. When completed, it will be the tallest timber building in the world. And many believe it'll point the way for how we should be constructing our cities in the future. Its name, Ascent.
I remember a structural engineer, John Peranto, said this building would change the way that codes are written. John, I don't know where you are. I thought you were being dramatic. I was wrong.
You probably heard the quote. I did say when we started this, if we get it built, it will change the code. It will.
To be able to create a building that will change the codes and rules that govern tall timber buildings here in Milwaukee has required the support and cooperation of some of the finest engineering talent from around the world. The city planning authorities, the fire department, even the U.S. Forest Service.
You know, it seems like when you're doing something really special and you believe in it, things just come together.
What inspired Tim Gockman was seeing a project for an 80-story concept design by architects Perkins and Will, Cambridge University, and engineers Thornton Tomasetti.
These projects that we do internally in the industry, these are really what spur innovation.
And the aim of this particular project was to see how far you could push the boundaries of timber construction with the innovative use of prefabricated components. They include glue-laminated timber beams, known as glue-lam beams, and panels made from cross-laminated timber layers called CLT. Collectively, they are known in the industry as mass timber.
It seemed like something out of the future. It was unbelievable. Not just the fact that you could do this to such a height, but that all the wood was exposed inside. And I sent it to the rest of the development team, our architect, et cetera, and we asked the naive question of, can we build a high-rise out of timber? I think Jason's been waiting for years for a developer foolish enough to ask that question, so he was pretty excited.
I would say a combination of excitement with a healthy dose of fear tacked on, because it had never been done.
Excitement and nervousness. I mean, it's one thing to do research projects, another thing then to actually bring it to reality. I would say River Beach was more of a research project than what you would call even a concept study for a project.
But if it could be achieved, the potential benefits are huge. Some estimates suggest prefabricated mass timber construction is 25% faster than a traditional build, reduces construction traffic by up to 90%, and cuts the people required on site by 3/4.
It is such a pre-engineered system that is done to a detail level that is not typically done for both steel or concrete, leads it to be much more complex.
The level of coordination that we were required to manage was like nothing we've ever seen before, because we digitally built this building down to the last screw. So it's been really, really eye-opening. And this is the way that buildings are going to be put together in the future.
Because of the concrete base and elevator shafts, Ascent is what is technically known as a hybrid, with timber making up 70% of the structure. Although high-rise hybrids have been built in Europe and Canada, this is the first time that anything even close to this has been attempted in the US.
In general, I mean, the mass timber frame supports the weight of the floor. So basically everything you're standing on in a wind-like condition where you have wind blowing on the building or you have, say, a seismic event, that is resisted by the concrete cores.
A really good example of the level of coordination that had to happen for this building to be built is driven by the fact that as the building goes up, the timber structure gets smaller and smaller because it's carrying less gravity load. However, the number of screws attaching the members stays the same. And so literally near the top of the building, we were running out of space in the wood for the screws to not clash with each other. And so the amount of coordination that it took to make sure that the connections were properly designed and free of conflict was hundreds and hundreds of man-hours by 3 or 4 different companies.
There are a bunch of theories as to, is it going to build faster? Is it going to be as precise as you believe it's going to be in the models and as others are telling you it's going to be? Yes, it was all theory.
Most developers wouldn't have the grit to really push on and do a project of this type. It's one thing to do something new, it's another thing to be the first.
It's probably not something a rational person's going to take on. We didn't realize how challenging it was going to be, and I think you need that for innovation.
Designing such an imposing wooden structure is one thing, but to bring the designs to life, you need to find people who can build it. But who do you need? The materials obviously points to carpenters. However, the building's size and structure requires the expertise of ironworkers, who became synonymous with the skyscraper in the first part of the 20th century. For contractor C.D. Smith, putting this team together meant consulting with workers and unions to create a new way for these established trades to combine their skill sets.
It doesn't matter if you're a carpenter, iron worker, or an office guy like I am. We all can have our opinions and thoughts, and maybe it's the right move, maybe it's not, but everyone does a good job of communicating, and everyone wants to get to that finish line as quick, as safe, and as cost-effective as possible.
They call it a joint venture. So basically, everybody does a little bit of everything, regardless of what union you're part of.
There's a lot of first times, a lot of people coming, introducing different ideas and different methods that we're going to adapt on the fly.
That beautiful wording.
Normally we set up a rebar and a pan and you pour a column and then you build a deck and you pour a deck. It's like concrete's like making cake. Wood's completely different than concrete. This is pretty neat.
If all goes according to plan, one of the benefits of this prefabricated design will be the speed of its construction and the fact that it will require an assembly team of just 12 skilled workers. However, the complexity of the challenge should not be underestimated. All very different from pouring concrete into molds. Even the most experienced of contractors could be forgiven for feeling a little daunted by the sheer scale of the kit of parts they are going to be working with.
Some are glued, some are straddled, it's wood on wood, some have a knife plate and there's bolts that go through the timber. And then you see the screw detail. There's a million screws and fasteners that hold the whole picture together. It's a big jigsaw puzzle.
And it's a jigsaw puzzle that requires the utmost precision.
Certain columns, in one face, there'll be 16 16-inch screws that hold it, and trying to fit them all in within the spec. Each screw has to be within 1.25 inches of each other, and then not hitting another screw as you're driving in.
Every screw has to go in at the perfect angle to make sure that the screw thread is in contact with the right layer of laminated timber, making up the beams and slabs.
Yeah, I'm learning every day.
And when it comes to positioning some of the columns, which require quick-setting epoxy resin glue, there is an added pressure of time before it sets.
And then when I say ready, it's rocket time. You got 8 minutes to set it. So and then you got to plumb it before the glue hardens too.
Every column has to be precisely vertical to fit with the floors that will follow.
You could set like 12 a day. We want to get faster than that. We want to do 24 a day.
For a building that has so many prefabricated elements, good transportation is going to be crucial. But project manager Chris Johansson is keenly aware this is one area that could easily wreak havoc with their tight schedule.
There's a lot of concern with the global shipping industry. With COVID, there's labor shortages at ports, there's labor shortages at rail yards. All of that combined into us just starting delivery of over 400 containers.
And then there's the weather.
Yeah, it's going to be coming very shortly.
If timber skyscrapers are to become a familiar part of our cities, there is one key attribute in particular that is essential they possess: endurance.
For anyone who doubts the longevity and durability of timber, look around me. 1060 and the timber's still here.
This is St. Andrew's Church in Greenstead, in the county of Essex in southern England. The oldest timber building in Europe. Like many churches, it has evolved and been added to over the centuries, but its thick timber walls date back over 1,000 years to a time when England was still ruled by Saxon kings.
The structure and shape and form of timber buildings was determined by the trees that were available to build the building. Engineers have to be able to calculate every part of a building. The challenge that we face is how to take this material and give it the uniformity and predictability that we need in our modern buildings.
The prefabricated timber structure needed to create Ascent is being produced in Austria. Almost half of the entire country is covered in forest, occupying an area the size of Switzerland. And with centuries of experience and an eye to the future, they are currently planting more trees than they harvest. The slower a tree grows, the denser its ring pattern. The higher the density, the greater the strength. It's for this reason that timber from the Ascent project has been selected from forests at a higher altitude where the annual growth is slower. One company, KLH, is making the CLT panels, whilst another, VHAG, is making the glulam beams and columns. Founded by a local carpenter over 170 years ago, VHAG has become one of the world's leaders in prefabricated timber structures. In their warehouse, timber destined for Ascent is stacked, ready to undergo a transformation that will enable it to meet the most stringent of criteria determined by the engineers.
Just to give you a picture, we produce for that building 2,300 cubic meters of glulam, but we have to pre-select 6,000 cubic meter of sawn timber. You see some of it in the background. From these 6,000 cubic meters, we selected only the best boards. We don't throw the others away, we just use it for other projects, for let's say normal projects. But the pre-selection process was an extra mile for the Ascent building, yeah, definitely.
Before the selection process begins in earnest, the sawn timber is kiln dried to reduce the moisture content down to around 10%. It then passes through a metal detector to ensure that there are no small pieces of metal that could damage the expensive and complex machinery.
Then there is a laser scan who checks how warped the timber is, because it might be a bit warped. And then we have an end grain camera to look on the annual growth ring, because we have to know if it's the right side or the left side of the board, and also how fast is the timber grown, so the thickness of the annual growth ring.
The timber is then planed and analyzed by X-ray to assess the density and to look for any resin pockets or cracks. Once they pass selection, every individual piece of timber is given its own data file containing all the information gained from this analysis. These pieces are known as lamella, which comes from the Latin word often applied to armor, meaning thin plate. Any weak parts of the lamella can be cut out and different sections joined together using a process called finger jointing, which greatly increases the surface area onto which glue can be applied. And as part of quality control, sample joints are regularly tested to destruction. The pressure needed to break the joint is equivalent to that generated by the weight of 30 tons. That's the same as a fully laden fire truck.
The single lamella can be endless. I mean, obviously, our factory has somewhere a limit, and that limit is 50 meters. And this thin lamella of roughly 40 mil is very flexible, so you can bend it to the shape of your architecture.
With the carefully selected lamella formed into the right lengths, they can now be glued and compressed together to make up the large beams and columns. Once dried, these are precisely cut to size using a CNC machine. It's only with the advent of computer-aided design that this scale of prefabricated mass timber construction has become possible.
Then you have, let's say, your perfect shape, and the last step is still a bit of manual work.
After a few cosmetic finishing touches, the steel jointing elements are added. Every detail is considered during the manufacturing process, right down to the loading of the shipping containers. The sequencing of loading is so complex, a special 3D load planning software is used.
By loading the container, we also think already on the installation process. So what element do they require first? And therefore, we place the elements in the right order already in the container.
Having left the factory, the beams and columns begin a 7,000-mile journey by sea to Port Milwaukee on the shores of Lake Michigan. Here, they are stored until their contents are needed on site. And when they are, it's down to Jesse Miller to ensure that they make the final 4 miles of their journey safely and on time.
Every single load, I think we're somewhere around 90 now, has been hauled by me. And as long as I continue, I should deliver the whole wooden structure, the whole building. It's definitely a proud feeling. I'm proud to be involved in this project.
You know, originally the plan was to have material at the Port of Milwaukee 2 to 3 to 4 weeks ahead of time, and then it would be ready for us. And with all of those, with COVID, Suez Canal, et cetera, those dates were getting extended out to where it was scheduling things down to the day.
Load 91, here we go.
Back on site and 11 weeks into the timber build, things are really starting to take shape.
Well, you gotta look way up now. So that's a big difference.
Handling the complexities of sourcing, procuring, and managing all the timber elements is Taylor Cabot and her team from Timber Lab, a mass timber design and construction company.
Can you imagine standing here in your living room, being surrounded by this wood? You know, it's gonna be a really rich, warm environment for people. Like, that view is just insane. This is why people pay the big bucks, right? There's absolutely no margin for error. We have 1,863 pieces, and they're all unique. If one of these fell off the side of the building, we wouldn't have a replacement for that piece. We would be asking for a new one to be made and sent to us. It's extremely critical that everybody is on board with understanding that these pieces are irreplaceable, and in some ways, you can't put a price tag on any of them. We've been extremely lucky, but I like to think that a lot of that is, you know, the hard work and dedication of everybody and having an amazing crew to put it together.
Taylor is no stranger to record-breaking timber buildings, having worked on the iconic 8-story Carbon 12 building in Portland, Oregon. When it was completed in 2018, it was the tallest timber building in America, standing 85 feet tall.
We were very proud of that, and we just beat it a couple days ago here on site. Feels good to actually surpass it. Somebody has to, so it might as well be me. We're blowing it out of the water, actually, which is pretty exciting as well, not to just eke it out with an extra floor. We're looking at about 7 days of floor right now. On a really good week, they've been able to do it in 5. They set all the beams on one floor in 1 day.
This is over a third faster than with a traditional build.
There would be no way to do that in any other material.
Such is the work rate that on average, one beam or column is lifted from the truck every 15 minutes. And every single timber component has to be assembled with the utmost precision.
Figuring out how to bring the pieces safely up to deck and set them to tolerances of 1/16 of an inch really requires an extremely thoughtful crew who understands that and has that skill set.
The most impressive thing is you give a guy a random task that he's never done before, and how quickly they can figure out, oh, if I do this or that, I'm gonna do it exponentially faster.
It took probably like 3 or 4 floors before we kind of got it down pat.
What are we on, 16 now? 16th floor?
As far as what we've learned on this project, I think is gonna say a lot as far as what's gonna start happening in the future.
I come home clean, so that's a good thing. Wife likes that.
Yeah, it's fun. Not like fishing, but it's fun.
We're here to make this project go, and I think, I personally think we're knocking it out of the park.
As ascent soars ever higher, It's interesting to note that Milwaukee is no stranger to record-breaking buildings. Just a few blocks away is the City Hall. When completed in 1895, it was the world's tallest building at 353 feet. In many ways, it's a mirror of its new neighbor. Its conventional structure, built around a steel frame, sits on wooden foundations made from over 2,500 white pine timber piles.
Yeah, it is ironic, the flip that you see right now with the use of mass timber on City Hall versus how we're using it on Ascent. But in some ways, you know, it's very similar. You know, we pushed technology pretty heavy back then with City Hall, but we're also pushing technology pretty hard right now with the Ascent project.
Today, we're obsessed with high buildings. They define our cities, but span, the space between walls, is just as important.
If mass timber is to be adopted on a much broader scale, it needs to be capable of supporting a wide range of structures essential to our 21st century infrastructure. At the same time as Ascent is being built, a huge mass timber roof is under construction as part of the ongoing renovation at Portland International Airport. For those involved in the design of passenger terminals, there is a sense that perhaps the wheel has turned full circle.
When King's Cross Railway Station in London was built in 1852, they used a laminated timber roof. It was 105 foot wide and 71 foot high. It was one of the engineering marvels of its time. No roof like that had ever been built before. But there was a problem because of the steam trains underneath this remarkable roof. The water vapor attacked the laminations in the timber, so it had to go.
The material chosen to replace it at the end of the 19th century was wrought iron, which had revolutionized the world of engineering, but would soon itself be usurped by steel. If laminated timber was to have a future, it needed to change. Andrew Lawrence is a structural engineer and timber specialist at Arup, a company which is renowned for its pioneering work in the world of engineering and construction.
The game changer is having a really good glue. It wants to be strong, but also it wants to be waterproof. And those waterproof glues were not invented until the 1930s. So right until then, we could, what we call laminate structures by taking small planks of wood and stacking them side by side or above each other. King's Cross Station, they're stacked horizontally, but they're not joined. They're not joined together. So it's like all the leaves of a book. They can all slide over each other when you bend the book. But if you glue those planks together with a really good, strong, waterproof glue, those leaves of a book become like a thick sheet of cardboard. So that's what those glues give us. We can essentially make much larger members.
So if we had the ability to create new, more resilient timber beams 90 years ago, why haven't we seen buildings like Ascent before?
One of the really exciting new developments is what we call CLT. It actually stands for cross-laminated timber. And the explanation of it is in the name. Wood is fibrous, and it only has strength in one direction. And so we take those planks, those fibers, and we lay those fibers in one direction. And then in the next layer, we lay the fibers at 90 degrees to that, and the same again and again. So we've made ourselves this cross-laminated timber panel, which has strength in two directions. And we can glue those together into very large panels. These panels might be 16 meters long and 4 or 5 meters wide. Now, this might sound an obvious thing to do, but it was only first done in about 1998. So actually really recently. And of course, it's taken time for the manufacturing capabilities to develop. So that's only been available to engineers and architects as a cheap building material for about 10 years. So if we've got these large panels, I mean, that's a game changer. With these CLT panels, we can use that as the floor or the wall of an entire building. You can imagine it like a giant piece of flat pack furniture. made out of all these wooden panels. And what we all know from making a piece of flat-pack furniture is we can assemble that really fast.
And CLT panels have the added benefit of being 4 times lighter than concrete.
Now, that can be hugely important in construction. So first of all, a quarter of the weight means that you've got at least 4 or 5 times less truck deliveries to site. Secondly, it means that we can save on the cost of foundations. And also because the wood is lighter, perhaps we want to build over a railway tunnel or something like this. Quite a lot of wooden buildings I think about have been built in locations where we couldn't have really built in other materials, or we couldn't have built such tall buildings in other materials because they'd have been heavier. And of course the extension of that is that if we want to add perhaps 1 or 2 stories onto a building, then wood can often be a lightweight way of doing that.
One of the biggest hurdles Ascent has had to overcome isn't one of engineering, but of perception. Could a tall building really be safe if there was a fire? And there is one fire in particular that occurred long before there were proper building codes to govern construction that has become synonymous with timber buildings.
The Great Fire of London of 1666 that started in a baker's shop in Pudding Lane spread throughout these timber buildings as far as the River Fleet. After the flames of the fire had subsided, to walk through the streets of London would have been utterly remarkable, because all the belongings of people had gone, the thatch on the roof had gone, but the timber frames survived the flames.
This ability of large timber members to withstand fire is something that would later be proved on numerous occasions in the large factories and warehouses of the 19th century.
And it's quite interesting that some of the code work and the code information we still have today is actually based on dimensions and sizes which came out of engineers looking at those fires.
Because of their extensive experience in this field, David Barber and the team at Arup were appointed as fire engineers for Ascent. One of the challenges they faced was that the existing building codes for tall buildings in Milwaukee were based on traditional steel and concrete construction methods. To make the case for timber construction, it was essential to work closely with those we turn to should the worst happen.
Often some of the really clever ideas we get to how we can solve some issues come from fire departments and the experience they have. We had a fantastic fire department who were enthusiastic about it, understood what was going on. So we want to have them involved, especially where it is quite innovative and quite different.
I was very pleased to be a part of it. It's great to have the world's tallest mass timber building in the state of Wisconsin, and more specifically Milwaukee in general. I think it's a big win for the city, and I think buildings of cross-laminated timber, mass timber, are going to change skylines in big cities forever.
With a fire, what's inside a building is every bit as important as the material used for its construction.
The majority of your heat is going to come from the contents inside the apartment. You know, we look at our consumables and our furniture.
Arup had already been independently conducting some groundbreaking research into how mass timber buildings react to internal fires.
We've been doing some large tests on very large compartments with exposed cross-laminated timber. We've been carrying those out in France, and as part of that, the process has been to work out how do fires react and change in larger compartments and larger spaces.
The tests have been able to help quantify to what extent exposed timber in a modern building will feed a fire once it's started.
In the same way that, we engineer for earthquakes and tornadoes and high winds and high snow loads and all those sort of things, as long as we know about it, we can then safely engineer for it. So it's a matter of understanding what the issue is, understanding what the data is, the sort of loads, and the way that the structure is going to be impacted, and then work out what are the mechanisms and levers that we have to pull to be able to design the structure to withstand that type of fire and that type of fire development.
Whilst the research has been invaluable, it was still not enough to instigate a change in building codes. Because of the unprecedented height of Ascent, it would need to prove that in the event of a fire, it would have the same structural integrity as a conventional skyscraper.
So we were absolutely looking at sort of something which was sort of breakthrough.
And to achieve that breakthrough, the timber columns would need to withstand a fire for at least 3 hours, which is more than 50% longer than previous comparable tests. The facilities and expertise needed to conduct them were to be found courtesy of the U.S. Forest Service at the world-renowned Forest Products Laboratory in Madison, Wisconsin.
We've installed the glue lamp column with thermocouples that allow us to monitor the temperature throughout the glue lamp as it's exposed to the fire. And it's well understood that char of wood forms around 300 degrees Celsius, so we can monitor that 300 degrees C isotherm through the depth of the column. And then by doing that, it enables us to calculate char rates.
Within 25 minutes, the temperature in the furnace will reach 1100 degrees Celsius. It's this surface charring that is key to timber's ability to withstand fire. It forms what is sometimes referred to as a sacrificial layer, which acts as a barrier to further combustion.
Once we obtain char rates from the glue lamp column, then structural designers can use those char rates to appropriately design the size of their glue lamp beams and columns within a building. It's incredibly exciting to be on the forefront of all of this and to watch these structures going up very close by to us. It's a really exciting time to be a part of this type of research.
In contrast, steel behaves in a very different way when heated to similar temperatures, which is of particular concern in an emergency.
In the case of a steel building, when that fireproofing falls off, the beam is allowed to be heated. We all know what happens to metal. When it heats up, it expands, and a 100-foot column steel I-beam will elongate approximately 9 inches at 1100 degrees Fahrenheit. Now, that might not seem like a lot, but imagine that 9 inches pushing out against the walls, right? So that's 9 or 18 inches on both sides, and that's going to cause significant stress and a lot of the catastrophic collapses like we've seen on these types of buildings.
What has reassured firefighters is that laminated timber behaves in a very similar way to those solid timber frames of centuries past. And although badly charred, it still retains its structural integrity. It's worth remembering that in modern buildings, sprinkler systems would do their job long before the need to depend on sacrificial charring. But 21st century construction codes are all about engineering for the worst-case scenarios.
We're looking at the structure in these fires, assuming that the sprinklers haven't worked, and these have reliabilities of 95, 96, 97%, so they're incredibly reliable fire safety measures. But we also start to look at, what if the fire department is delayed, they can't get to the building, so we kind of rule them out as well. So we're looking at, very, very sort of low likelihood fires and looking at the worst case situation for those. And then we have to work out, so what other mechanisms and levels of safety do we have to put in place? In addition to sprinkler systems, we have automatic fire detection systems which sound alarms and which allow floors where the fire is closest to be evacuated first. We have certain systems which protect stairs with pressurized air and they keep the smoke out, and often they're within corridors as well so that people can leave their units and within a smoke-free environment. And then also we have lobbies for people who can't walk downstairs, and we have protected spaces which allow people with disability to be able to wait safely for the fire department to come and take them away. And often people have no idea that those systems are actually there. They hear fire alarms and they maybe have an idea that there's a sprinkler in the building, but often there can be a multitude of other firefighting systems of water supplies and tanks and pumps and all sorts of other systems which are in place and backup power supplies to make those systems incredibly reliable so when they are needed that they do work. And that's the most important thing. And modern high-rise buildings have those fire safety measures.
Look at the brown of the wood. It feels good to see that, right?
This is the future of construction.
This is Brian Brashaw and Steve Kennan, who work for the Forest Service. Their role is not only to look after the nation's forests, but to also promote the sustainable use of timber.
Forests make everybody's lives better. 70% of all the water in the United States comes from forested lands. So clean water, clean air, wildlife habitat. They support rural economics, they support jobs, they absorb carbon dioxide. and they convert that into carbon.
For every 1 ton of its dry weight, a tree will have absorbed 2 tons of carbon dioxide.
Our mission is to maintain a healthy and resilient ecosystem. Healthy, resilient forests are critical to our way of life.
Around the world, it's estimated that 1.6 billion people heavily rely on forest resources for their livelihood.
All of the trees that we're looking at are storing carbon. But we also have the ability, when a tree is harvested and used for a value-added product like cross-laminated timber or mass plywood products, structural composite lumber, those kinds of things, we have the ability to store that for another 100 years or the life of that building itself. So that's a long-term storage.
At a time when many forests are under threat from climate change, non-native invasive species, and catastrophic wildfires, if demand for timber dramatically increases, will that mean we'll deplete this vital natural resource? The good news is that Brian, Steve, and their colleagues from the U.S. Forest Service believe, as counterintuitive as it may seem, that the opposite will happen. Their research suggests that increased demand for timber will incentivize good forest management and provide the funds with which to do so.
When we manage forests, part of management revolves around harvest, as we remove some of those trees to create healthy conditions, to be a healthier forest, to be more fire resilient. And those opportunities to store carbon in harvested wood products or in the forest are certainly better than seeing the carbon go up in catastrophic wildfires that we face nationally. We have incredible opportunities to naturally regenerate, to plant. The United States has a wide diversity of forest types and species. And we have more forests than we've had at any time in the last 70 years.
So biodiversity matters. Why does it matter? Because if we have all of the same thing, if something goes wrong, then all of the same thing gets wiped out. It's important for us to have different species, different age classes, old trees, young trees, and actually areas where there's few trees, but there's more grasses and other things that grow symbiotically with trees.
To help create what they believe will be a win-win scenario for forests and a sustainable construction industry, the U.S. Forest Service has been proactive in the promotion of responsibly sourced timber.
The Forest Service has invested in mass timber since 2014. Part of that is education. We need to make sure that engineers and architects and construction firms understand this material, how they can design with it, and how they can build. And then market development. We have a Wood Innovations program that I manage that supports early stage investments, and those investments can support engineering and design.
We're trying to diversify. We need to have as many markets as possible. The more markets we have, the more management we can do on our landscape. What it does is it expands our ability to manage our landscapes.
In the case of Ascent, a proposal came in to evaluate and provide early stage engineering and technical assistance advice as they were planning this project. And I think even today, I just get really excited as I saw this building going up, the ability to walk through it, you know, the ability to put out and touch, right? I mean, typically you don't think about touching a concrete column or hugging a concrete column. And certainly a place I'd love to live someday. You want to hug it? I know you do. All right, good.
Anything that can be made from wood, we can figure out how to do it here. We know how to use 100% of that tree. We don't have to waste anything. We have the technology to do it right now, today. And that's really important for people to understand. We can utilize the materials that come from the forest and regenerate more forests behind that. So as you take a tree, you grow a tree, or 2 or 3.
One area of research that the laboratory has been conducting, which could have huge benefits for the construction industry, is in the field of nanocellulose technology.
Well, cellulose is a major component of wood. And so we're taking this component down to its smallest scale.
And at its smallest scale, it has remarkable properties. It's lightweight, stiffer than Kevlar, and has a tensile strength 8 times that of steel. And when it's used in concrete, the crystals enable the cement to bind differently, making it much stronger.
The amazing thing about this material is you can reduce the amount of cement needed to have structural performance by about 20%. And so we're testing that now out on a bridge out in California.
It also has the potential to form a basis of a much lighter and stronger alternative to glass, which is not only 2/3 more thermally efficient than glass, but also has structural properties.
We're still working out some of the features of this to get it to be completely transparent, but we're 90% there.
And because nanocellulose has the ability to conduct electricity, if a combination of chemically treated and untreated fibers are incorporated into flooring, when they come into contact through compression, they produce electricity, which means that floors in places like busy hallways could produce significant amounts of energy.
So we can build a building, the structural components from wood. We can put flooring down that's wood, even ceilings. And now the windows, and have that produced from a wood product. And what if we could then take another byproduct from a wood process, such as in pulp and paper making, the lignin, and we can produce an insulating foam. Now we've increased the carbon storage in that building considerably. A plant-based organic building whose component parts can biodegrade easily and go back into the soil to benefit the soil as organic material, or it can be dissolved in sunlight and seawater. Then we would have a truly sustainable system.
As timber construction enjoys a growing renaissance, just what heights could a timber building reach?
So, if we're making a building entirely out of wood, then the optimum height is about 10 stories. If we get above that sort of height, we're going to struggle to make it strong enough to resist wind loading. The walls and columns supporting that building are really going to start to get quite big. So it's above about 10 stories that it makes sense to start to combine wood with other materials.
Which is why Ascent, with its 25 stories, has adopted this hybrid approach.
You're going to see hybrid systems with steel as well as concrete that really allow you to get the full aesthetic and almost biophilia of the space of exposed wood, yet use steel where it makes sense.
Whilst it's unlikely that we will ever see a timber building as tall as one of John Paronto's other projects under construction, the 1-kilometer-high Jeddah Tower, it is at lower heights where the true potential of timber can be fully realized.
We talk about the glamorous tall buildings, but the majority of what we build across the world is smaller buildings. And just imagine if the majority of those could be built out of wood. Imagine how much carbon dioxide could be locked away inside those buildings. The best thing we can do, whatever we build our buildings out of, the best thing we can do is make them last as long as possible. From a sustainability point of view, there is nothing worse than demolishing a building. All that effort and energy that's gone into building the building is thrown away. Now, conventionally, we talk about 50-year design lives. I want to change that. I want us to talk about 100-year design lives, even 200-year design lives. But obviously, there will come a point where that building has reached the end of its life. The next step is, can we reuse the components from that building in a new building?
And the beauty of a prefabricated mass timber building is that it is far easier to dismantle and do just this. But possibly the most extraordinary vision for a sustainable building is a recent award-winning proposal from Guestline Architects in Ukraine. Their idea is to create a living skyscraper, which integrates genetically modified trees as part of the structure. As it grows, they envisage their living skyscraper could connect with nearby buildings, forming a green network over an entire block. Back in Milwaukee, the full 25-story height of Ascent has just been reached. It's known in the industry as topping out, and as is tradition, it's something to be celebrated. Just 6 months after the first timber was installed, and having shaved a third off the construction time for a traditional build, the final CLT slab is being signed by those involved in Ascent's construction.
Everything went great. That's about it. You guys have a good day.
Still feels a little bit surreal to be standing here and looking at that.
This is proof that tall timber works, unequivocally, and that is going to truly contribute. Changing the way that buildings are designed and built. There are people not just in the United States, but throughout the world on social media sending their congratulations or discovering Ascent for the first time because so many people are sharing images of us topping out.
The phone is ringing. People want to know how it got done. Can they do it? And so we're looking at timber projects in 3 or 4 other states right now. Our hope is to be doing these basically all over the country.
So when people look at Ascent, I hope they're inspired. I hope they can see that there's a way to build a more beautiful product in a more sustainable way.
Would you do it again?
In a heartbeat. We're doing it again right now.
We're going to do it again, and hopefully we're going to do it multiple times.
On paper, at least in the city of Milwaukee, we could build a timber building up to 420 feet tall.
A project like this out of mass timber will definitely help the industry move forward, and just because it hasn't been done before doesn't mean you can't. It feels like we're on top of the world. It really does. It's great to see timber reach these heights.